We present PIE-NeRF, an efficient and versatile pipeline that synthesizes physics-based novel motions of complex NeRF models interactively. In traditional NeRF pipeline, NeRF is optimized pixel-wise using a set of multi-view images and finally generate neural 3D scenes. However, synthesizing physics-based dynamics remains less explored, which is our key motivation to develop PIE-NeRF, a meshless physics-based dynamics generator allowing users to interact with the scene in a physically meaningful way. Same as classic NeRF, we first use multi-view images of a static scene as input to train our instant NGP-NeRF. Then an augmented Poisson disk sampling is employed according to the gradient of density field to model the geometry of the 3D shape. After Voronoi partition, we obtain our quadratic, generalized moving least squares kernels and integrator points for simulation. When we are integrating across a ray in a deformed space, we warp the ray to undeformed space if it go through a integrator points cuboid. As time integrates, we can generate a multi-view physics-based dynamics. We first show our Lego excavator whose shovel is applied with an external force. Our method is able to render the generated dynamics in different views. We allow the cars move under the influence of gravity and inertia, eventually resulting in a collision. Our method is able to handle codimensional shapes. QGMLS can generate a smooth and soft cloth dynamics, while linear GMLS suffered from locking issue. Our method is capable of accommodating various physics parameter settings, leading to distinct visual effects. When rendering the deformed scene, linear ray warping tends to generate artifacts, while the quadratic warping used in PIE-NeRF accurately fetches the color information and produces more plausible results. PIE-NeRF can be applied to any elastic model like as rigid as possible and neo-Hookean, the latter of which can maintain constant volume. We can edit the particles and kernels to cut the sculpture, which then falls on the floor. We can also compute the depth map from NGP-NeRF and generate the moving shadow using shadow maps. We have designed an interactive user interface, and GMLS kernels can also be visualized as the colored ellipsoid. Users can adjust kernel size to capture fine-grained motions such as local deformation and interact with NeRF scenes like applying external forces and position constraints. We benchmark our method against deforming NeRF for shear and squash deformation. We directly modify original mesh vertex positions to generate ground truth and deformation gradient field for deforming NeRF and PIE-NeRF. Our method consistently demonstrates better performance, evidenced by lower MSE values and higher PSNR scores across all cases. We employ standard finite element method as the ground truth for comparison with our method. Dynamic results are produced using the same boundary conditions, physical parameters, and external forces. Our results are quite similar to the ground truth, despite minor differences arising from error accumulation. We last compare our method with PIE-NeRF, which also combined physical models with NeRF-based representations. We can observe that PIE-NeRF fails to capture high-frequency geometric information. The ship's mast broke due to the capture of incorrect geometric information. PIE-NeRF fails to map material points back to their rest pose positions accurately due to excessive interpolation smoothing between particles and grid cells, which leads to overblurred results.